Now that we've gone over the basics of hexadecimal and disk geometry, you're beginning to see the dynamics of how data is stored at the microscopic level, so to speak. As digital forensic examiners, we need to understand the science of how data is stored for the same reason that a forensic pathologist needs to understand the physics and physiology of the human body. With a microscopic, low-level understanding of how the body functions, a pathologist is able to tell whether someone was possibly poisoned or just simply died of natural causes. He or she could also tell whether or not a deceased victim had consumed alcohol shortly before the time of death. Likewise, with a microscopic, deep-down view of how data is stored, we can possibly tell if someone had attempted to delete files, alter dates and times, or even hide data from those who are attempting to look for it. Yes, there are a lot of programs that automatically do this with the click of a button, but these programs only carry out what they're programmed to do in a systematic fashion. Programs can miss things. There's no replacement for human skepticism and nuance in a forensic investigation. If I may give an example, I was told by a detective recently that keyword searches do not always catch what you're looking for. Keyword searches are one of the principal tools used by many digital forensic applications on the market. The detective told me that he was working a case involving child pornography where a keyword search of the suspect's forensically imaged hard drive was not yielding any evidence. After continued searching, it was discovered that the suspect had hidden his folder filled with pornography deep within the file system structure. The folder was also given a mundane, generic name so as not to draw attention to itself. Since the perpetrator used those protective measures, general keyword searches did not find anything. The evidence was found on a hunch, based on how the file system works. Generally speaking, anybody can be trained to use a tool such as EnCase or FTK. All you have to do is memorize a particular sequence of buttons and menus and make sure you select all the right ones. What separates trained button pushers from digital forensic specialists is the ability to analyze subject matter at the file system and hexadecimal level, and, if necessary, perform certain tasks manually. The purpose of this video is to give you an introduction to file systems, and to demonstrate some basic navigation of an NTFS formatted disk within a disk editor. Let's begin. A file system functions in much the same capacity as a librarian does within a library. File systems are what allow us to interact with the data that is stored in our long-term storage media. Without them, hard disk drives and flash memory would be seen simply as a giant blob of unallocated space. In order to better illustrate this analogy, I want you to imagine the following. Imagine going to the library to pick up a copy of George R.R. Martin's Game of Thrones. You walk through the door, where you're greeted by a librarian who asks you what you want. You tell her that you want the first book in Martin's series, A Song of Ice and Fire. While you wait, the librarian immediately goes to the exact shelf on the other side of the library and then retrieves the book for you, all within a matter of a few moments. Now picture this alternative scenario. You go to the same library to pick up the same book, only there's no librarian. As a matter of fact, there are no shelves, no indexing, and no guidance. All of the available books are thrown into a large container in the middle of the library. Your book is here, somewhere, among all these other books. You just have no idea how to get to it. This is what our file systems and our computers do for us. They store our data for us and make it available for us at a later date. The file system also shows us how much space is left in our storage devices. Much like a traditional library, the file system indexes, alphabetizes, and keeps track of the status of everything that it has within its boundaries. Without it, your storage media would be viewed as a single block of unmanaged space. You could have a hard disk with 275 gigabytes on it. You could have 250 gigabytes worth of data stored on that drive. Without the file system, that hard drive would be viewed as 275 gigabytes of unmanaged space. Even with all of your stuff there. That would be similar to the image I conjured of having all your books dumped into a single large container when you need to find one in particular. In this circumstance, how would you be able to get to your data? Your single book that lies in the middle of the pile? The answer to that would be data carving, but that is a topic for another lecture. There are a large number of file systems in existence currently. As examiners, you will more than likely come across some more than others. Mobile forensics is a separate block of instruction, but for the sake of lecture, two of the most common mobile file systems are YAFS, which stands for Yet Another Flash File System, and HFSX. YAFS is the default file system that is used for Android phones. HFSX is generally used with iPhones. When it comes to desktop and laptop computers, two of the more prevalent file systems are FAT and NTFS. FAT stands for File Allocation Table. There were three different varieties of FAT in general. There was FAT 12, 16, and 32. FAT 12 was used with floppy disks, which were the earlier forms of media storage. FAT 16 was used for storage with early hard disk drives around 1984. FAT 32 was introduced with a later version of Windows 95 and by default in Windows 98. The 12, 16, and 32 stood for the size of their respective entries into the allocation table for data storage metadata, among other things. NTFS stands for New Technology File System. It was released as part of Windows NT back in 1993. It became the default file system around the year 2000. Since that time, it has remained the primary file system for most Windows-based platforms. NTFS is a journal-based file system which revolved in large part around a centralized database known as the Master File Table, which maintains metadata for each and every single file and folder on a hard disk. There's another file system known as the Resilient File System, or REFS, which is supposed to take over for NTFS in later versions of Windows. Currently, it's part of Windows Server 2012. From the viewpoint of the forensic examiner, if you exclude mobile phones, you will see NTFS more than any other type of file system. It has been the file system in use from Windows XP up to Windows 10. Every once in a while, you'll come across a Windows 98, 95, or even a Windows 3.1 machine. But this will be rare in today's society. If you become a digital forensics examiner, you'll still have to know how to analyze all of these older technologies, including floppy disks, for the reasons I mentioned previously. In the following section, I'll demonstrate mounting and navigating an NTFS image file. This is Activate Disk Editor. This tool allows you to view physical computer disks or forensically collected image files. There are a number of tools that allow you to do this, such as WinHex, HXD, and Disk Explorer, just to name a few. One of the reasons that I chose this tool is because that it comes with a number of ready-made templates to visually interpret meaningful information from the disk. Every tool of this kind comes with a number of similar features. Namely, the ability to navigate the disk environment at the hexadecimal level. You can jump to a desired location anywhere on a disk by cluster, sector, or even byte level offset. I'm going to do a simple demonstration of opening a disk and doing some basic navigating to various points on it. After this demonstration, you should be able to start your own basic analysis of a forensic image file. I will also be pointing out some aspects of the New Technology File System, or NTFS, that you'll see in this environment. As I have said previously, NTFS will be the type of file system that you'll see most frequently as an examiner. This excludes mobile forensics, however. there are some noticeable differences between laptop and desktop computers. In order to truly learn how a file system functions, you need to actually get your hands dirty and go through one yourself. There is only so much you can learn from studying high-level diagrams of how files are managed at the disk level. We're going to be opening a physical disk, but first I'll show you how to open an image file. To load a forensic image file in this tool, click on the button labeled Add Disk Image. When the Open Disk Image window appears, navigate to the location where your image file is stored. This will be a file type with an extension of usually .dd, .raw, or .e01. When you've selected your forensic image file, click OK. This will add the image file to a list similar to the one you currently see here. After the file has been added, you'll be able to open it by right-clicking on it and selecting Open in Disk Editor. To open a physical disk, such as your C drive, right-click on the item in your list and click Open in Disk Editor. For this demonstration, I'm going to open my backup drive, which is the 3 terabyte Western Digital hard disk desktop drive. This is the same drive that I mentioned in the introduction to this video. Before you begin to navigate the disk, you need to do a few administrative things first. If it is not already activated, you need to go to View, Windows, Templates in order to activate the pre-designed templates on your screen. After the Templates window has appeared on the left side of your screen, go to the drop-down list at the top and select Master Boot Record. This will make the colorized Master Boot Record template active. Next, find the Navigate button at the top of the screen and select it. From the drop-down menu that appears, select Partition Table. If the option does not appear as Partition Table on your screen, it will probably be listed as Master Boot Record. If your hard disk has a GUI ID partition table, it might even say that in your list. It depends on what your selected hard disk has as its partition scheme. If your hard disk has a GPT, then you'll need to change the template's drop-down menu to GUI ID partition table. If you follow the steps that I mentioned previously, using Master Boot Record as your guide, then you should see something similar to what is currently on your screen. If you see something different, then you either did not choose Master Boot Record as your template scheme, or your disk has a GUI ID partition table and not a Master Boot Record. This is where I'm going to stop this current video demonstration. The navigation and NTFS demonstration portion will be in the next video. For now, make sure that your computer screen looks similar to mine. If not, find out what you did wrong and make adjustments. I'll see you in the next video.